Before we get started with this material, I just want to ask you to keep something in the front of your mind, and that's we're going to be introducing some new terminology, definitions, things like that, but most of the actual mathematics that we're going to need to handle these new ideas and exercises really come from what we learned just prior to this. The ideas about increasing and decreasing functions and what I've called in the past the increasing decreasing chart. If you can do that material and understand that material, you have essentially all the tools that you need to do this material, no matter how it looks when you first see it. So I want to give you some advance warning that some of these things may look overwhelming when you first see them, but if you'll just give them a chance, you'll see that you already have the mathematical tools you need to do this. This is especially true when working with polynomial functions, which I've mentioned many times are continuous on their whole domain. Domain's the set of all real numbers, and they're very well behaved. So when you're dealing with polynomials, this is extremely straightforward. Occasionally you'll get something that's not a polynomial and you might have to think a little bit more, but the ideas are not that bad. So having said that, let's go ahead and get started with this material. In this lesson, we want to look at some of the things we've learned earlier. This is sort of building up to what we want to talk about in this lesson, which is how to take the tools and learn about the relative and absolute extrema of functions, that being the maximum values of functions and minimum values of functions. I'm going to start off talking about relative extrema. When I use the word extrema, you can think maximum, minimum. One extreme is the maximum value of a function, another extreme is the minimum value, the highest and the lowest. Those are the extremes. In math and in a lot of real-life applications, it's going to be important to find out where a function reaches its maximum minimum value, and it turns out that what we've been doing has built up what I like to call a toolbox of things that we can use to answer these sort of questions. For instance, if I look at this simple graph here, you can see that the function increases on the left and decreases on the right. And that tells us that that value between the increasing and decreasing is a maximum for this function, at least locally in that area, and we call that a relative maximum. In the area of that point, which I'm calling a critical number, this function reaches its highest point. Conversely, in an interval where the function is decreasing on the left and increasing on the right, then this point, which I've labeled another critical number, is a minimum value of the function, at least locally in that area. That's the lowest point on the curve. The first critical value in that area around that critical number, that's the highest point on the curve. Those are called the extreme values. So it sort of gives you a visual and an intuitive understanding of what we mean when we say relative extrema, or relative max, or relative min. We'll be using that term relative max, relative min quite a bit. When you lump them together, you call them extrema. Relative extrema includes the max and the min. I'd like to just take a minute or so now to try to emphasize, or maybe it's re-emphasize, what we're trying to do here and what our tools are. I can make a formal definition, but I'd really like to show you the pieces we've already talked about individually, how they're going to help us do what we need to do in this section. If you have a function f that's defined at some value c, and the behavior around c based on what the derivative of the function is like this. Namely, that the derivative is negative. Remember, less than 0 means negative. If the derivative is negative to the left of c, that means that you have a negative slope, which means the function's decreasing to the left of c. And then if the behavior changes to the right of c so that the derivative is greater than 0, which means positive, positive derivative means positive slope, which means the function is increasing to the right. So if you have a decrease in slope, which is the derivative, to the left, and an increase to the right, you have something that we call a relative minimum of the function. Decreasing to the left and increasing to the right. At the value x equals c, you have the lowest point of f in that interval around c. On the other hand, if the behavior is reversed so that the derivative is positive to the left of this value c and negative to the right, that means we have a relative maximum. An increasing slope followed by a decreasing slope. That's like a peak. So around c, you have the highest value of the function at the value x equals c. A lot of this is vocabulary too. The maxes and mins, the relative maxes and mins taken together can be called relative extrema. If you have a single one of them, you can call it extremum. One of them, an extremum. So if f of c is a relative extremum, meaning it's either a relative max or relative min, then we say that that extrema occurs at x equals c. Again, just basically vocabulary. The f of c value is the relative max or min, and where it occurs is the x equals c value. And a problem might ask you for both, or it might ask you to find the relative max or min. That would be the f of c value. It might just ask you to find where the max or min occurs, and that would be the x equals c value. Conversely, if you have a relative max and min at a value x equals c, then that x equals c is certainly a critical number of the function. This is extremely important. Make sure you take the time to make this a part of you, not just memorizing definitions, but understanding what it's saying. Decreasing followed by increasing is the sign of a relative minimum. Increasing followed by decreasing is a sign of a relative max, and as you'll see later, it's possible that you get neither. Now, once we determine that c is a critical number of a function, we have something called the first derivative test for relative extrema that helps us to classify the function value at that critical point as being either a relative minimum, a relative maximum, or it could be that it's neither. And you need to build up an intuition about how this works. I'm going to lay out the first derivative test, and then we're going to work some examples to try to build some intuition. If f is a continuous function on some open interval from a to b around a single critical number c, in other words, this number c is inside of this interval a to b. If f has a derivative on that interval, except possibly at the point itself, then that value f of c can be classified as either a relative minimum, a relative maximum, or neither. If the derivative is negative to the left of c and positive to the right of c, then it's a relative minimum. If you look at what I've done here on the right, you can see that if f prime is negative, that means the slope is negative. I've drawn an arrow angling down to the left. On the other side of c, the derivative is positive. That means it's sloping up to the right. And if you look at that shape, you can see that it's the shape of a minimum. So if you find a critical number and you test the derivative on the left and it comes out negative, and you test the derivative on the right and it comes out positive, you know that you've located a relative minimum of the function. On the other hand, if it's reversed, if the derivative is positive to the left and negative to the right, then you found a relative maximum. And again, graphically, you can see I've drawn in the point x equals c, and if you plug into the derivative and you get a positive number on the left, and if you plug in a value to the right of c and you get a negative for the derivative value, then you know you found a relative maximum. And if it doesn't go down, up, or up, down, then it's neither a max or a min. Here's some ways to look at this and sort of get in your head some visualizations that'll help you see what we're talking about. Here's the case where c is a relative minimum. You have a function that going from left to right dips to a minimum and then starts back up. You can see on the left side the derivative is negative, and on the right side of c the derivative is positive. That shows you that you're at a relative minimum at c. If you flip it upside down, you can see the behavior has changed. Now, if you look at the derivative to the left of c, it's going up. That's a positive value of the derivative. And it's going down on the right. That's a sign of a relative maximum. Down, up for the derivative is a minimum. Up, then down is a max. It's possible that it does neither. If you test around a critical number and you get positive on both sides, or you get negative on both sides, then you don't have a max or a min. It's a critical number that is neither a maximum or a minimum. Having those pictures in your mind is important to get some way of thinking about this visually. Before we actually start working problems, it's probably good to talk about just some basic guidelines for finding these relative extrema. First thing you want to do is take the derivative. Anytime you're dealing with increasing, decreasing, you take derivatives. And we've just seen from our earlier discussion that these increasing and decreasing also tell you about maxes and mins. So you want to find the derivative. Then you want to use that derivative to find the critical numbers. And then you're going to use those to determine your test intervals, as we've been doing earlier. And remember, your critical numbers come from taking the derivative and setting it equal to 0, or finding where the derivative is undefined and making sure those values are in the domain of the function. Third step is to create some kind of, I call it an increasing decreasing chart. It's what I like to use, or if you go back to what the text does, they build a table. But it has the same information in it, and you can find those important pieces that you need for this either chart or table by plugging test values from each interval into the derivative and looking at the sign. If you plug a number into the derivative and it comes out negative, you know you've got a decreasing interval. If it comes out positive, you know you have an increasing interval. And then finally, for every critical number, you're going to use this first derivative test, which we just discussed, to classify something as either a max or min or neither. Okay, that's the basic idea. Let's actually go through this. Suppose I have this function f of x equals x to the fourth minus x cubed. The first thing I know I'm going to do is take the derivative. It's a polynomial, so it's an easy derivative. It comes out to be 4x cubed minus 3x squared. I know I'm going to set that equal to 0 at some point to find the critical number, so I might as well go ahead and factor it now. I notice there's an x squared in both terms, so I can factor that as x squared times the quantity 4x minus 3. If you set that equal to 0, you set each factor equal to 0, so you either get x squared equals 0, which gives you x equals 0, or you get 4x minus 3 equals 0, which gives you x equals 3/4. If you get good at this, you can just look at that and see what the critical numbers are without having to actually do much written down algebra. Those critical numbers divide the number line up into intervals where you need to check for increasing and decreasing behavior. So you put 0 to the left of 3/4 because 0 is smaller than 3/4, and then you create test values in each interval. So you want to look at some number smaller than 0. Why not just choose -1? Some number between 0 and 3/4, maybe say a half, and then some number bigger than 3/4, why not 1? So those are the test values you need to use. What do? A test value is for testing. So you take each test value and plug that value into the derivative. In other words, you're plugging in here. So you take -1, do the calculation. I'm not going to belabor the arithmetic, but you end up with -7. You really don't care about the numerical value that it's -7. All you really care is that it's negative. So I'm going to just note that -7 is a negative number, and I'm going to put a negative sign inside that interval from -infinity up to 0. Then you move to the next test value. Well, the next test value is a half. If you plug a half into the derivative, again, we're plugging right in here into the derivative. Again, arithmetic's fairly easy. You come out with -1/4. I don't care that it's -1/4. I just care that it's negative. So I'll put a negative sign in that interval. And finally, I move to the third test value, which is at 1. Plugging 1 in, you get 1. Again, I don't really care that it's 1. I just care that it's positive. So I'll put a positive sign in the third interval. Now that's behavior that I wanted to come to grips with in this problem. Where's the function increasing or decreasing? Because I know the increasing, decreasing tells me about whether I have maxes or mins. So looking at that chart and thinking back to what it means to be a relative minimum or relative maximum, it's the behavior around those critical values. So if you look at those negative signs, remember those were plugged into the derivative, and that tells you about the slope. So to the left of 0, the function's decreasing, so I sort of arrowed down. Between 0 and 3/4, it was still decreasing, so I arrowed down again. Once it passed 3/4, it starts up again, so I arrowed up. And if you look back at that behavior, remember that you get a sign of a relative minimum when you get this down, up. Down on the left, up on the right. That's the signature of a minimum. So we know that we found a minimum at 3/4. But there isn't one at 0 because it doesn't go down, up, or up, down. It goes down, down, and down, down, or up, up tells us that there is no relative extrema there. There's no relative max, there's no relative min. The ideas are simple, but you have to practice. Practice makes perfect. To actually find the value, which is what we call the relative max, in this case the relative min, what we call those things, you get the y value. So once you found that the critical value that produces a minimum is at 3/4, you still have to plug 3/4 back into the original function, back into the original function, and do the calculation. And I won't do it here. I show it, but I'm not going to talk my way through it. It comes out to be -27,256. And remember, that number, -27,256, was obtained by plugging back into the original function, not into the derivative. So be really careful about that. So now I've used the first derivative test plus all the tools that I learned in earlier sections to find that I have a relative minimum at 3/4, -27,256. If you actually looked at the graph, you can see it. At this point, 3/4, -256, you have a minimum, decreasing on the left, increasing on the right. The point at 0, 0 is a decrease, so it's not a max or a min. You need to have an intuition about what you're doing and some kind of idea in your head, a picture of something, what's going on with the graph. Okay, relative extrema, those are local phenomena. Now we want to talk about a function and the absolute extrema, the absolute maximum, absolute minimum. Well, what does that mean, absolute? Absolute is like a global property. Absolute max, absolute min is global. Relative is local. And I think maybe this might help you understand the distinction between relative and absolute.
look at this chart. It shows you that the highest point on Earth is Mount Everest. We would call that the absolute maximum. Globally, over the whole Earth, that is the highest point. On the other hand, if you look down a little further, you can see that Mount Fuji, although not nearly as high as Mount Everest, is still the highest point in Japan. That would be a relative maximum. In the local area, Mount Fuji is the highest point. But globally, Mount Everest is the highest point. Think about that. That's the major distinction. Absolute is looking at everything, what's biggest, what's highest for maximum, or what's lowest for minimum over the entire function. Whereas relative, you just look at the area around it. So you can have a local max or local min and go somewhere else on the function and find another one, or maybe something totally different. But you're only looking locally when you're looking for the relative. You're looking all over the values of the function when you're looking for absolute. Again, I'm going to put up this definition, but again, it's not something to be memorized. It's something mainly to be put back as a reference. All it's saying is that a function value is an absolute minimum if that function value is smaller than every other value on the whole interval that you're looking at, everywhere, not just locally. And it's an absolute maximum, this function value at C, if the function value is bigger than every point on in the whole domain of the function. So intuitively, you can see why this works. I'm going to make one more shot at helping you get this distinction right because it's so important. If you look at this figure, the function has a relative maximum here, but it has something even higher. The function's only defined between A and B, so it has an absolute maximum that's higher than the relative maximum. Having an absolute maximum doesn't preclude having a relative maximum. But the relative maximum could actually be the absolute maximum. It would just have to be higher than any other point on the curve. On the other hand, if you look at this point is the lowest point on the curve regardless. So in the local area, it's the lowest, but over the entire interval from A to B, it's also the lowest. So that point would be a relative minimum, but it would also be an absolute minimum. Not only is it the lowest point locally, it's the lowest point globally over the entire interval from A to B. Think about those things and try to get that distinction down because it'll be helpful. And again, going back to the Mount Everest example, it's the same. In the same sense, we could say that Mount Everest is both an absolute max and a relative max. In the area around Mount Everest is the highest point. That makes it a relative max. But globally, it's also the highest point, so it makes it an absolute max as well. And as I said, that relative maximum is not an absolute maximum because there's a point on the curve that's higher. Give that some thought. This next result points out that if a continuous function has a closed interval as its domain, and I put brackets here just to emphasize that's a closed interval, then it must have both an absolute minimum and an absolute maximum interval. And the key thing here is it's a continuous function. So it's like a piece of string or a rope that's not been cut. If you take a piece of rope and lay it out on the floor, and you can make it wiggle any way you want to, but if you lay it out and create an XY axis where it sits, then there is going to be an absolute highest point and an absolute lowest point. in the way you set it up. If you think of this as a rope that's not cut, it's just a continuous rope, there will be, and you're only looking on a closed interval from A to B, there will be a highest point and a lowest point. That's all that's saying. And it's called the extreme value theorem if you want to give it a name. Another important point here is that these extrema, the max and the min, the absolute max and min, can occur at the endpoints. Like here, the endpoint, this B value, is where the absolute maximum is. Whereas on this one, the relative max is not the absolute max. It didn't occur at the endpoint. The endpoint on A is not the lowest point on the curve. You've got an absolute minimum over here. So all I'm saying is, when you're talking about absolute extrema, you have to get the relative extrema as well, but you also have to throw in the endpoints, because the endpoints could be a place where the absolute max or min occurs. So you have to take the relative extrema, get those, and then you have to throw in the endpoints. Always, you have to throw the endpoints in when you're looking for absolute extrema. All right, what about some guidelines? And then we're going to work some problems. If you want to find the extrema of a continuous function on some closed interval, you're going to find the critical numbers, just like we did in the earlier problem. Then you're going to take those critical values and find their y values. In other words, when you say max and min, you're talking about y values. When you say something's a maximum, you're talking about height. So the heights are represented by the y values. So when you evaluate a function at those critical numbers, what you're doing is finding how high those critical values go on the function itself. And then you want to evaluate the function at the endpoints, because like I said, the endpoints could be the highest or lowest point. So not only do you find the relative extrema, you also have to check those endpoints as well. Once you've done all that, though, just put them in order, in numerical order of y values, and whatever comes out smallest is the minimum, and whatever comes out the biggest is the maximum. So once you get them all those y values calculated, you simply put them in order. The smallest y value becomes the minimum, the biggest y value becomes the maximum. For example, if I ask you to find the absolute minimum and maximum values of this function f of x equal x squared minus 6x plus 2 on the interval from 0 to 5, then the first thing you would do, of course, is to find the critical numbers, and that involves finding the derivative. So you take the derivative. That's a simple polynomial. It's going to be easy. So f prime of x is 2x minus 6. Then to find the critical numbers, you find where the derivative is equal to 0 or where the derivative is undefined. And for a polynomial function, there's never any problem with it not being defined. So the only place a critical number will come from for a polynomial function is when the derivative is equal to 0. So if you set that equal to 0, you'll see that 3 is the only critical number. If we were looking just for the relative max or min, that's really the only thing you have to worry about. But because we're looking for absolute and we're on a closed interval, when you make your increasing decreasing chart, you have to make sure that it ends at 0 and 5. It doesn't go on forever. And then you have to check those y values at the endpoints, because one or both of them might be an extrema, in addition to what might happen at the relative value. But once you get that increasing decreasing chart drawn correctly, as I have done here, you go back to the same thing we were doing earlier. You want to take a test value in each interval. And remember, it's got to be between 0 and 3. You can't jump outside that interval, because we're only interested in values between 0 and 5. And then you want to take a test value between 3 and 5. So I chose 1 as being my value between 0 and 3, and I chose 4 as being my value between 3 and 5. And remember, you're testing them in the derivative. The derivative tells you whether the function is increasing or decreasing. If you plug 1 into the derivative, you get -4. again, you don't care about it being -4, you just care that it's negative. And then if you plug the other test value in, you get 2. Again, you don't care really that it's 2, you just care that it's positive. And you can see now that that behavior is decreasing on the left, increasing on the right. That's the signature of a relative minimum. So there's a relative minimum at 3. And to find out what that minimum is, you take 3, and you always go back to the original function when you're calculating y values. And you'll find out that the y value is -7. But because we're looking for absolute extrema, we have to test endpoints. Remember, we have to throw in endpoints. So one endpoint is 0. Plug 0 back into the function itself, and you get a y value of 2. Then take the other endpoint, 5, you get a value of -3. So what you want to do is you want to take all three of these and put them in order of their y values, smallest to largest. So if you do that, you'll see that at 3, the -7 is the smallest of all the y values. At 5, you get the next smallest, which is -3. And so the biggest is the one at 0. So I put them in increasing order of y values. And once you do that, the smallest y value is the absolute minimum. The largest y value is the absolute maximum. So the absolute minimum is -7. That's the lowest point on the graph between 0 and 5. And the absolute maximum is 2. That's the highest value on the curve between 0 and 5. It's nothing difficult about this, but it does take practice. You've got to go through this again and again until it becomes second nature. If you wanted to look at the graph and see that it confirms what we've just written here, you can see I popped up the graph in the upper left-hand corner. And you can see that, and these endpoints get thrown in too, and you can see that the maximum is going to be here and the minimum is going to be here. And it confirms what we did algebraically and using our calculus. This example I chose just to show you another tricky aspect of some of this. You just have to be careful and watch out. The simplest problems are super simple, but as soon as you bump the level of difficulty up, sometimes you get some things in there that are a little bit tricky, and you just have to think about them so that you've seen these tricks a bunch of times and they don't surprise you anymore. So I've got a different function now. H of t is equal to t over t minus 6, and I'm interested on the closed interval from 7 to 13, and I'm looking for the absolute extrema. That means I have to check the endpoints as well. Still go through the process of doing the relative extrema. So that means I need to take the derivative. It's the quotient rule, so you'll do the low d high minus high d low over low squared. And I won't bore you with the algebra, but you'll end up with something fairly simple, minus 6 over the quantity t minus 6 squared. Now what do you do with the derivative? You're finding the critical values. The critical values, the critical numbers, are what you get by making the derivative 0 or undefined. Well, what makes the derivative 0? Notice the numerator of that fraction is minus 6. How can you make a minus 6 equal 0? You can't plug anything in for t and make minus 6 equal to 0. So there aren't going to be any values. There aren't going to be any values where the derivative is equal to 0 because the fraction has a numerator that's just a number. You can't make it 0. And you know you can't make the denominator 0. So there's not going to be a critical value coming from setting the derivative equal to 0. How about the derivative being undefined? Well, obviously there is a place where the derivative is undefined. It's at t equals 6. But remember also that a critical number has to be in the domain of the function. But it might have been worth noting just from the very beginning that you can't divide by 0, so there's no way you can let t be 6. So as soon as you see this 6 right here, you say, aha, that's not even the domain of the function. So although it makes the derivative undefined, it's not a critical number because it's not in the domain of the function. It's just something you have to keep in mind as you're doing this, and you just have to always think about that. In any case, if you call it tricky or not tricky, it is something you have to consider every time you do a problem like this. So there aren't any critical numbers here. But we have a theorem that says that if you've got a continuous function defined on a closed interval, and you say, well, this function is not continuous at 6, but 6 is not even in the interval. 6 is over here. That's another reason t equals 6 couldn't work. You could also throw it out because the fact that it's not even in the interval that you're interested in. 6 is not even between 7 and 13. So that's yet another reason you could have tossed it out. So there just are no critical values or critical numbers. So the only endpoints, the only maxes or mins absolute are going to come from the endpoints. You have the extreme value theorem that assures you that if you've got a continuous function, and this function is continuous as long as you stay away from 6, and the interval from 7 to 13 does stay away from 6. So it satisfies the extreme value theorem. So you know there's going to be a max or a min absolute, but it'll just have to be at the endpoints. So you take the left endpoint, plug it back into the function, and you end up with 7. Take the right endpoint, 13, plug it back in, you'll end up with 13/7. 7 is bigger than 13/7, so it's the absolute max. 13/7 is smaller than 7, so it's the absolute min. I pointed this out in particular as being tricky. I'm not sure it's really any trickier than the one I worked just before, but however you want to classify the trickiness of these problems, making sure that you don't try to put something in as a critical number that's not even in the domain of the function is important. And also, if you get something that's not in the interval of interest, you can toss it for that reason as well. Practice makes perfect. The more you do these problems and come across these things and learn from your mistakes, the better off you're going to be when you get to the test. I always want to translate these things back to ideas about what the graphs look like under these conditions. So I just want to move to a question like this. What if I ask you to pick out a graph of a function that satisfies these 4 conditions? One of the conditions is that it has a relative minimum at x = -1. It has a critical number at 0 but no extrema. It has an absolute max at x = 2, and it has an absolute min at x = 5. And these are your 4 choices. You want to find the one of those 4 that satisfies those 4 conditions. I would just take those conditions one at a time and go through them. That first condition says the relative minimum is at x = -1. Well, you know what a relative minimum looks like. It's going to have that behavior of decreasing and then increasing. So you're looking for something that looks like that. The second condition says there's a critical number at 0 but no extrema. Remember, you have no extrema at a critical number when it doesn't go down, up, or up, down. It either goes down, down, or up, up. So it would either be that down, down behavior, down and down, or up and up. That's what the behavior around x = 0 would be. And then when you say something has an absolute max at 2, all you're saying is that that's the highest point on the graph in that interval you're interested in. And when I say it has an absolute minimum at x = 5, I mean that it's the lowest point on the graph. So those 4 conditions have to apply to only one of those graphs. And the first thing I think I would probably notice is that those first 2 graphs have exactly the opposite behavior at -1. Notice at -1, you're supposed to get this down then up behavior, and this is the actual opposite. That's up and then down, up and then down. So neither of those graphs can possibly be right because they don't satisfy this first condition. What about the second condition? The second condition says that at 0 it either goes down, down, or up, up. But this graph shows at 0 going up and then down. That's not right. At 0 it's not supposed to do that. It's either going to be down, down, or up, up. So the second condition knocks out the third graph. Well, what do you think now? You've only got one choice. You're only left with one possibility, but let's look at it more closely and make sure that it really does satisfy. So I'll go back to the first condition. Around -1, you're supposed to get that down, up behavior, and you do. You get down, up, down, up. At 0, you're supposed to either get down, down, or up, up, and you do get up, up, so that's good. Third condition and fourth condition just tell you about the highest and lowest point. Third condition says that you have a highest point at x equal 2. And if you look at x equal 2, you indeed have the high point. And at x equal 5, you get the low point. And again, that seems to be true. So obviously, that has to be the correct answer. And it's nice to be able to think about these things graphically and see what these conditions imply about the behavior of the graph itself. Let's do an application. I chose something involving the maximum profit. If you're given a profit function, and in this case it's the profit for selling X burgers, and we want to find the sales level that gives us maximum profit, that's something we talked about earlier. The derivative of the profit function is called the marginal profit. So you want to take that derivative and set it equal to 0. That gives you the marginal profit. You're going to set that equal to 0, but it's easier to rewrite that middle term. Instead of dividing by 20,000, think of it as multiplying by 1 over 20,000. Dividing by 20,000 is the same as multiplying by its reciprocal. That's easier because now you can just use the power rule. So when you take the derivative, you'll get 2.44 minus 2 20,000ths x. And of course, 2 20,000ths is the same as 1 10,000th. And you want to set that equal to 0. That's the marginal profit. It's just a polynomial function, so there won't be any values from anything from derivative being undefined. So you just have to set the marginal profit equal to 0, solve for x, and that comes out to be, through the algebra, 24,400. So you're going to get maximum profit if you sell 24,400 burgers. Technically speaking, you should go through this test about checking on both sides of it. But since there's only one critical value and it's an application problem, it's almost a formality. You know, I suppose you could get a problem where someone was trying to trick you and say there isn't one. But in general, in an application problem with one critical value, it's going to be what you're looking for. And then the last step is to take that x value and plug it back into the profit function and find out what that profit would actually be. So you're going to take it in and plug it into the profit function. And you get, after quite a bit of kind of yucky arithmetic, you'll get $24,768. So if you have that profit function, your maximum profit from selling a certain number of burgers comes at selling 24,400, and it gives you a profit of $24,768. Practice, practice, practice. The principles are simple, but they do take some getting used to, and I don't know any way of getting better at it than just practice, make mistakes, find those mistakes, correct them, learn from them, practice some more. By the way, that's what the function would look like. And you can see at that value we found, you would have the maximum profit of $24,768.